So, once upon a time, I was a physicist. And the previous talk, thank you, it was amazing. Reminds me of something when I think of physics. I like to think about old physics because if we want to draw a parallel with the kind of science we have, we think we need to go back. When Newton came up with what's now known as the laws of dynamics, he was absolutely hated by the people who were the academics of this time. He was using tools that were absolutely not understandable. He invented differential calculus, him and Leibniz. And this was not tools that people were using. And there was a big debate. And in the start, he was losing this debate. And the only reason he eventually won that debate is that his tools were useful. They were able to predict something. And to continue on this, I sometimes put this on my slides, but I removed it. I think one of the really interesting things about what Newton did is that he could draw the link between prediction on Earth, throwing things, basically, dynamics on Earth, but also celestial movements. So a kind of generalization that links things that do not seem obviously linked. And if I think about the success of new tools, I think about that. That wasn't planned, but the previous speaker, Gael, raised those thoughts. Okay, so I want to talk about things that relate a lot to many things that have been said before, so I'll try not to be boring. So the kind of questions I'm interested in. So first, yes, I'm more of a computer scientist these days, statistical person, boring people. So the kind of things I'm interested in is, so with imperfect theories, and I'll define a bit what I mean by that, how ambitious can a model be and yet stay grounded on evidence? And that's really important to me. And that goes back to the points that Carl was making, is that everything we do is loaded with values, and that massively shapes the research that we do. So what can we do? What kind of questions can we ask? And what I would like what I would like us to reflect on as a field is how to avoid inflated expectation on theories and models. Because those inflated expectations then loop back in the kind of value system of our field, and then in the kind of sociology that happens, and I think that pushes us to maybe dead ends, or at least slowing us down. Okay, so I got into brain sciences a while ago, and I found that something was really fascinating is that, we have imaging data, and imaging data has brought a huge amount of data. So neuroscience and psychology have become data intensive. And really, the opportunity that I saw is that we can measure and characterize really well the object of interest. Now, as a reviewer, as a reader of paper, as an editor, at some point I really got tired by the fact that a lot of the field is driven by incomprehensible data processing. I say this as a data processor. Incomprehensible mathematical modeling, statistical methods, and I can't tell if a paper is right or wrong, actually, even though I'm supposed to be the statistician who knows AI and data science in the review committee. So when we think about data and the brain, I think that the right parallel is that of astronomy. We're looking at the object we're interested in, but we're looking at it from a very far distance, and it's really hard to intervene on it. So the ideal experiment would observe all the neurons and be able to intervene directly on them. Maybe. I mean, what would we do with this? Would we get any kind of understanding? I don't know. I said that we had imperfect theories. What I want to say by this is that we don't have, an overarching theoretical framework. The theories that we have only explain a limited domain of observation. So in the Kuhnian, view of things, I think we're a pre-paradigmatic science. So this is what I mean by imperfect theories. So, given this, I'll ask the question again. In this setting, how ambitious can a model be and yet stay grounded in evidence? And so this is what I'd like to talk a bit about with the point of view of statistical person who's, let's say, not very conventional in statistics. So I'll first, describe a bit and mostly repeat things that have already been said, how we confront theories to empirical evidence. And then I'll do a few bold claims on how we could rethink modeling. And I need to keep time in mind. So, first thing, general, maybe oversimplified point of view of how we do statistical evidence in science. We do some modeling, we model the system, we may craft an experimental manipulation, we model the data. We do all this based on our understanding of the theories and construct of our field and of a data collection. Actually, we do this based on our theories and construct. I said of the field, but that's not true. That if a theory is not accepted everywhere, we typically use ours and not the others. And so, that's going to depend on a field-by-field basis. And then we do statistical inference, which is that we fit what we've done before on the data, typically, doing maximum likelihood. This is the kind of stuff that statisticians like me like. And then we reason based on the model and its parameters. That's the paradigm of statistics. It's related to what's been known as statistical modeling or probabilistic modeling that has been really pushed forward by Sir David Cox, who was a very famous and well-respected statistician. So, well, we've mentioned this. Brain imaging is very hard to model. You're not going to give a simple model on it, but we try. And so the way we work, you all know this, is that we craft an experiment that will probe the mental process we're interested in, and we're typically going to do one elementary psychological manipulation, and we're going to do an opposition between the two. We're going to call this a contrast, for instance, and we're going to reason on the opposition. Now, this is done with brain imaging. It's sometimes done with reaction time. So this is really the standard way of doing things. And what's underlying between this is that there are cognitive models. For instance, we mentioned just before the visual system, how we decompose the visual system is going to lead us to specific oppositions. Okay, and for everything to work, well, we need to design the right task and stimuli that recruit the right mental process, and ideally the opposition used should balance well the nuances. I stole this from Russ Poldrack, by the way, many years ago. So in the visual system, we've seen just before, people have over time crafted all kind of different oppositions and revealed different things. And the point is, if we ask a stupid question, we get a stupid answer. We can build a car versus something experiment, and we could definitely have statistical evidence for a car-specific region or Lego-specific region or something like this. So Russ asked this question many years ago. So what does this tell us? It tells us that without proper constructs that we put in our statistical model, our statistical model is unable to allow us to give useful conclusions, which as a statistician is incredibly frustrating. So I'll claim that this is because we're reasoning on model parameters. The fact that we can do statistical testing on a model doesn't establish in any way the model validity. And this is how brain mapping works. It's done via doing statistical testing on the parameters of a linear model. And that's a fairly fundamental thing if you think as a statistician. The validity, well, the meaning of your parameters is fully conditional on the model. Change the model, the parameters mean something else. And if the model is based on an invalid construct, it's useless. And so there's an extra problem, is that operationalizing the constructs is very hard. And so a few years ago, Russ and many others ran the NARPS, a study which, at least to me, frightened me a lot. Not that I'm very surprised, it's been done in other fields. But, having different people analyze the same data leads to massively quantitatively different results. And it's because we need to operationalize those constructs. And even with the same model, what we call model in fMRI, the specific set of model, even with the same fMRI model, using different software leads to brutally different results. So even, instantiating this mathematical but slightly conceptual model into an actual estimation leads to a lot of difference. So what I want to say here is that there is, in my opinion, no correct model that is going to be given by an oracle or an expert. Typically, statisticians get away with this. They say, a domain expert will resolve this problem. That doesn't exist. So, an extra problem, sorry, I'm going through all kinds of challenges of our field. An extra challenge of our field is it's full of overgeneralization. Full of untested generalization to new domains or to causal claims. I will claim that our field is riddled with causal claims that we don't really say because we know we're not allowed to. But one of the reasons why I realized this is that talking to people, they always came back to using brain imaging because they wanted interventional targets. Now, that is clearly a causal goal. I think it's fine. We need to accept it. Now, to the debate of simple versus complex models. Truism, the brain is complex, and I think simplicity just won't cut it. We end up with a patchwork of simple theories that do not suffice to give us a reasonable big picture. If we study these things in isolations, we have a forest of facts, but we can't relate them for ontological reasons. We don't really know if the study has asked questions on the same problem or not. But also, even without this, because we don't know how to balance those effects. I can't combine two different effects because the effects have been studied only by an opposition, and I only know that there's a statistically significant difference in this double dissociation. I don't know how to weigh things. And this is, by the way, this is not only in neuroscience, this happens in all kinds of social sciences. And to me, it seems like a dead end. If we can't do this. We need to move forward from this. Now, I don't know how to move forward from this, of course. And to make things worse, all the constructs of the mind are probably oversimplifications. Useful oversimplifications, but oversimplifications. So, intelligence. Now, I know that there is, an infinite subdivision of intelligence. And it's probably a useful construct. But there's probably not one intelligence, not five intelligence. It's probably a useful construct that's intrinsically multifaceted and fuzzy. It's still useful, but it's not like temperature. These days, in physics, temperature is a very precise definition. I don't think intelligence or attention will ever have this. Okay, so to kind of summarize this, the way we integrate evidence in cognitive neuroscience is focused on significance rather than signal fit, though there are, of course, the young guard that is doing a bit more of this. And it leaves the door open to wrong models, because statistical testing, I don't think, can rule out in any way a model that is wrong. Now, what's a wrong model, of course, is a big question. One of the problems is, from a statistical standpoint, is that to be able to do statistical testing, we need a well-posed model. And by construction, the well-posed model must be very simple. We can't do statistical testing on very complicated statistical models. And so it requires us, the tool that we have, the statistical tool that we have, requires us to distill a problem to a very simple one. And so, my agenda is to abandon well-posed, simple statistical model, embrace messiness and high dimension. And of course, I approach this agenda with the tool of machine learning, of statistical learning, which is basically, just to define it, it's basically statistics, but not for testing model parameters, but for prediction. And there's a continuity between the two. And I think but what's underlying my talk is that those statistical tools, I think, are having an impact, reshaping how we can do science. and exposing a battle between the old guard and the young guard. We want understanding. We just had this discussion. So, a few proposals on how we could rethink modeling. And the two key points that I'd like to make is prediction and causality. First proposal is that we should judge outputs and generalizations of models rather than their ingredients. I strongly believe this, back to the point I was making about Newton's dynamics. And this is not what's happening, by the way, currently. The way papers are reviewed is by looking at whether the ingredients of a model is correct. Now, of course, we can't just suddenly change the way we review papers. And the reason is that we don't have enough statistical power. And the models, everything is so undetermined that we need to put a lot of validity burden on the modeling parameters. On the modeling ingredients. But I think we need to move forward. We need to tackle larger data sets. We need to tackle more diverse settings, and to start looking more at predictive validity. And this is pretty much the methodology from the machine learning or AI world. So the classic way of reasoning I've presented is model-based reasoning. We can do some reasoning based on model outputs. I take a model and I wiggle its parameters, I change things, and I see how the output changes. And there's more and more statistical tools that allow you to do things like this, including causal inference. And there's a third way of reasoning, which is sometimes known as warranted reasoning. It's the kind of reasoning that you can have when you do randomized controlled trial. I don't believe my models. I don't believe I have a reasonable understanding of what's going on, but because I am intervening in a very special way on my system, I have statistical guarantees of certain things. I just wanted to point this out. It's not something that we can always do in neuroscience, but in terms of reasoning with black box science, it works. So, quickly, we mentioned the visual system, and one way to move forward from dichotomies has been mentioned before. It's using convolutional neural networks, as has been mentioned several times today. So that's one example of things that we can do where we're using prediction of models rather than ingredients. Another problem is the problem of reverse inference. Once again, rest is fine, eat this, where the challenge is to find what mental processes are supported by a given brain structure. And the challenge here is really to somewhat invert the inference, because the problem is that we're manipulating, or the experimental manipulation implies the observed response, and we'd like to the converse implication. And here, there are different challenges. One of them is that the kind of claims that we would like to have are claims of high-dimensional statistics. The reason is that there are many brain regions, and if we want to go from brain to behavior, we need a model with many, many brain regions. And so we were, again, outside of our comfort zone in statistical framework. And another challenge is that this requires data on many mental processes. And so we embarked in this a few years ago using machine learning to predict, mental process, or rather task, from brain. And here we hit a problem, which is that we were convinced that it was useful to predict behavior, or some representation of behavior, across paradigms, across cognitive paradigms. And here we hit the problem. It was very difficult to describe the different cognitive paradigms in the same words. So that's the ontological problem, but also that this description, we didn't know how to weigh things. Was one experiment more attentionally loaded than another? And so here we're really hitting the problem that we don't know how to build a model that models many, many things jointly. And here, what I think was useful was to try to generalize across study. Okay. The second part of the proposal can we develop canonical operationalizations of constructs? So here, in a sense, we're revisiting psychometrics. Oops. Nope. And I think where we can revisit psychometrics is to say we're going to operationalize those constructs using empirically tuned or machine learned, it's the same thing as far as I'm concerned, proxies. We no longer have to have simple models for those constructs. How general can that be? I'm not certain, but I can give you two examples. One is that of aging. Aging is not the same thing as age, right? You know, some people are older than their age, and some people are not. And so what we and others did is that they predicted chronological age from brain, and so they get what's known as a brain age, and then they show that the discrepancy between the brain age and the chronological age is actually a useful measure of health. And I like to call this a proxy, a brain proxy of aging. And it's fairly black box, right? It's a machine-learned brain proxy of aging. And so we've done this in other problems. We've done this for neuroticism and fluid intelligence. Once again, what we're doing is we're doing machine learning. We're taking a canonical definition, and we're predicting it. And the interesting thing is that sometimes, not always, but sometimes what we call the proxy measures, so the brain neuroticism, the brain age, yada, yada, actually correlates better with behavior. And this can be explained, you know, it's the part of neuroticism that the brain explains. Okay, so just to wrap up on this, I think actually working a lot on we should work more on our constructs. What I presented here was just a small thing, and I think there's much, much more to be done, because if we don't work better on operationalizing, I should say we should work more on operationalizing our constructs, because that completely breaks our framework. And finally, last one, I think we need to think more about causality and interventions as first-class citizens. We mentioned this. Most of the time when I hear understanding and I work with people, I find that eventually they want an intervention. Not always. I mean, there's basically two kinds of understanding. Understanding for storytelling, and I don't want to be dismissive. Storytelling is extremely important. This is how we teach. This is how we talk. And understanding for intervention. We can do counterfactual reasoning and causal inference on black box model. It's a statistical theory that's been increasingly developed. It does require you to open some aspects of the black box, but not every aspect. And the big problem to me is that of extrapolation, and a causal model will extrapolate much better than one that is not built on causal associations. But if you want to extrapolate really across domains, strongly across domains, you're not just extrapolating from a brain image to another brain image. You might be extrapolating from fMRI to EEG to you want to extrapolate outside of your, you know, closed box of data, closed world of data. And here you need to find features, you know, variables that you can put in your model that bridge those domains. And here the constructs come back because it's the only thing that are going to be really, really generative. So constructs allow you to write models across domains. And so, you know, my proposal, my conjecture is that a good construct is one that gives the model that generalizes best because you can causally anchor your model on this. Now the problem is, you know, causality means intervention. I can't intervene, well, it's not ethical for me to intervene on the intelligence of someone. So we're in a really difficult problem here where the pure construct is not available. And if we think a bit more about this, the challenge, and we're kind of, you know, we've kind of circled back, because the challenge is that of construct validity. If we have imperfect and correct construct validity, this will break down all the framework. So basically what I'm telling you is that I've started by saying, I need to focus on prediction and I can get away with other things. I'm actually looping back and I'm saying, well, it's going to help, but it's not going to solve everything. Okay, I'll wrap up, but I just want to stress that the statistical toolkit that we're using, I do not think is adequate to compare very different theories or to work with theories where we have a very hard time controlling the ingredients. And I think that we need to focus on reasoning from model outputs, and I claim that black box models are good for science. And I will stop here. Thank you.